Hello once again, and we have yet another question from AS level physics, AS2, cover 2011, and the summer exam in June. Question number 5. So this is all about Young's double slit experiments, and let's read together what it says. So figure 5.1 illustrates an arrangement to observe interference. Laser light is incident upon an opaque slide on which there are two transparent slits, S and T, and the light transmitted through these slits is initially in phase, overlaps in the region between the slits and the screen, and the resulting interference pattern is observed on the screen. This is the standard setup for our Young's double slit. We have laser light coming into the slide that has two slits on it, and the screen then is a distance away, where we'll then have the interference pattern appearing here. So let's read what the first question is. This arrangement ensures that light emerges from slits S and T is coherent. Explain the meaning of the term coherent in this context. What I would like you to do is to imagine the wave coming out of S, just like this, and the wave coming out of T, just like this. Now, by coherent, we mean that, as you can see with these, that the crest is coming out exactly the same time as the crest here, and we could even, if we imagine we pull that back a bit to a trough, perhaps. The same is true for this here. It would be a trough that's coming out at exactly the same time. So how do we get this to happen? How can we get it so that they're coherent, that the crest comes out at exactly the same time as the crest here, and it repeats itself exactly in time? Well, we need to have them with the same frequency. We need to also have them in phase, and for that to be constant. So those are the two things. That has to be frequency and constant phase. So let's move down to the question. Put in our answer. On as if by magic it appears the waves from S and T are the same frequency and constantly in phase. Part B then. With the arrangement, light emerging from slits S and T is in phase. Explain the meaning of the term in phase in this context. So perhaps I've already explained this, but we'll go for it again. What we mean is that the light coming out of S, whenever a crest comes out of S, a crest comes out of T. If it's a trough that's coming out of S, then it's a trough that's coming out of T. They are in step with one another, and we can put that down in our answer down here. Kablam! There we go again. The part of the wave emitted from S is identical to the part of the wave emitted from T. For example, a crest coincides with a crest. Let's move to part C. The interference pattern obtained on the screen is a sequence of bright dark fringes as shown in figure 5.2. And by considering the paths followed by the light from slits S and T, explain the formation of a bright interference fringe. So by considering the paths, explain the formation of a bright interference fringe. So why do we get these bright patches? It's really what it's asking us. Let's bring them down over here, and this is going to be our wave from S meeting the middle point here on the screen, and this is going to be our wave from T meeting our middle point on the screen as well. Trying to make them in phase so our crests are coming out at the same time. Now it's the same distance from S to that middle point as it is from T to that middle point, and for us to get a bright fringe then we have to have constructive interference, and as you can see, the crest from one is meeting the crest from the other. Now that explains this center fringe here, but what about the rest of these fringes? Where do they come from? Well, let's go back to the diagram, and I have slightly shifted the waves there, but we still have a crest from S meeting a crest from T. So we'll have constructive interference, we'll have a bright fringe there. So a bright fringe here, because a crest is meeting a crest, and we'll also have a bright fringe here because a crest is meeting a crest. Now the path though for T to get to here is different than the path to get S to there, and if I just take each of these waves, you'll notice something there, that the number of waves that it took S to get there is 1, 2, 3, 4, 5, 6, 7, and the number of waves that it took T to get there was 1, 2, 3, 4, 5, 6, 7, 8. But the difference between the paths was one complete wave, so that meant that a crest was still meeting a crest, and that's the second thing that must happen for us to have our bright fringes, is not only is constructive interference, but the path difference between each of the two sources will be a whole number of wavelengths. We will then have not just a bright fringe here, we'll have one up here. We'll actually have one in here where a trough is meeting a trough, and on the same here and here. Let's go over then to the question, fill out the answer. Blam! There it is again. At a bright fringe, constructive interference is happening. So our crest meeting crest, troughs meeting trough, etc. And the path from S to the screen must be a whole number of wavelengths of difference than the path from T to the screen. Part D, to end with, on the interference pattern obtained, the distance between the centres of 7 bright fringes is 24.3 millimeters, see figure 5.2. The laser light has a wavelength of 6.42 times 10 to the minus 7 meters, and separation of the double slits S and T is 0.66 millimeters. Use the data to determine the distance between the double slits and the screen. So using this information, we've got to find out what's the distance between the double slits and the screen, and it is a distance of D that we're trying to find. Now, what do we know? Well, it says there that the centre of 7 bright fringes is 24.3. Scroll up to see that. So our bright fringe here, that's 1, 2, 3, 4, 5, it's 6 fringe separations, 24.3. So we can fill that in as our fringe separation. 24.3 divided by 6 to get the separation of 1. Wavelength of 6.42 times 10 to the minus 7. And a slit separation of 0.6 millimeters. Let's just quickly show you what we mean by all those numbers. So our distance D is from the card here with the 2 slits in it to the screen. That's what we're trying to find. Our Y is the separation between 2 fringes, between one and another. So we've got 7 of these. So there's 6 fringe separations. So we divide that by 6. The wavelength of light is from the laser light. And the last thing is the distance between the 2 gaps here, the 2 slits, is 0.6 millimeters. The relationship then between all of these, if we zoom in, is wavelength is equal to the distance between the slits times the fringe separation divided by the distance between the slits and the screen. In the numbers we then have our wavelength of 6.42 is equal to the slit separation, so we put times 10 to the minus 3 to make that all the same unit of meters, for millimeters 2 meters, and then 4.1, which is the 24.3 divided by 6 times 10 to the minus 3 as well to get it into meters, all divided by D. You rearrange that equation then for D, and you'll have bring D over to the other side, so multiply both sides by D, then you'll have to divide both sides by 6.42 times 10 to the minus 7 to get the D on its own, and that ends up to be D is equal to 4.16 meters. Put that in there, 4.16. Right. And let's zoom out and see all our answers. There we go. Mark scheme. How did we get on? Tick.